Welcome back, class. So today we are going to start our discussion of Chapter 18. So Chapter 18 will serve as sort of a follow-up to Chapter 17. So we're going to start out talking about a few topics that directly relate to acid-base chemistry. And then we're going to close out the chapter by talking about some other types of equilibrium beyond acid-base equilibrium. So let's jump right in here and talk about what we did in lab, which was do a titration. So a titration can look for a lot of different things, but probably the most common form of titration is an acid-base titration. And so in an acid-base titration, you have some solution, either the acid or base, of unknown concentration, and you have a solution of known concentration, and you're going to add these together until you reach the end of the reaction, right? And so we'll talk about ways that we can monitor this. Now, technically speaking, if we go by the definition, we say that the solution of unknown concentration, might call it the titrant, would be added to the solution of known concentration until the reaction is complete. Now, of course, we don't have to do it in that manner, right? We can add the solution of known concentration to the solution of unknown concentration, right? The reaction is still going to take place in the same way, and oftentimes we will do that in a manner that is convenient. So, for example, in lab, we had our known concentration in our burette, right, what we're adding, because that was the convenient way to do it. We had a large quantity of that liquid of known concentration that we could put in the burette, and we had a relatively small volume of what our unknown was, in this case, our acid. So it doesn't really matter what you add to what. The key is you have to keep careful track of something that you're adding and to then pay close attention to when the reaction is complete. Now, when is that reaction complete, right? Now, for an acid-base titration, we mark completion as what we call the equivalence point. And the equivalence point is when the moles of acid are stoichiometrically equal to the moles of base. So in other words, we have equal moles of acid and base in our reaction flask. Now, what this means is that both the acid and the base have been mutually, if you will, neutralized, right, by doing this. And so if we think about our reaction, right, we have our acid mixing with our base, and at the equivalence point, the only thing that's there is water and some ionic compound, right? So we got that idea. Acid plus base gives you water plus a salt, right? It's a neutralization reaction that's taking place here. Now, we often follow this reaction or this type of titration with what's known as an indicator. And we'll talk a little bit more about indicators as we go through this section. And it is a material where it has a color change during pH changes. So in other words, it exists as one color at one pH and a different color at other pHs. So at some point during the titration, right, it's going to change colors. And so we're going to, as we see, pick an indicator that is going to undergo that color change at our equivalence point or close to our equivalence point. So we can see sort of a prototypical titration here where we have in the beginning, in this case we have it set up to where our acid is in our flask and our base, right, is in our burette. And we're going to be adding our base to our acid, and during the course of this process we're going to be neutralizing the acid in our flask, right? We're going to be undergoing this neutralization reaction. So, of course, in the beginning part of this titration, right, we're going to be at a very acidic pH, or at acidic pH, because we have predominantly acid in our flask. As we neutralize the acid away, right, we're going to stay in that acidic, solution. Now, the acidity is going to go down, or meaning the pH is going to go up, because we're lowering the concentration of the acid as we neutralize it. But at some point, we start to see this color change of the indicator. And this particular indicator is phenolphthalein, right? A very common indicator for these acid-base titrations that we use in a lot of labs. And so this is the indicator that you would have used in the Ka of a weak acid lab, right? That you're going to use in that lab. And so initially, right, we can start to see just, little bits of pink, right? And then it typically would go away with stirring. Now, once you reach, quote, the equivalence point, right, where the solution is neither, the acid and the base have been neutralized, right, we're going to see that color change where the solution goes from colorless to a nice pink color. And so where we can use that color change to indicate that we've reached the equivalence point of the titration, that point where the reaction is complete. Now, during this process, we can either plot as we go or gather data that will allow us to plot what we call a titration curve. And this is a plot of pH versus volume. So the pH is going to be on our y-axis, the volume added from our burette is going to be on the x-axis. And we're going to see an inflection point during this curve, and this is where the equivalence point will occur, right? Is at this inflection point. Now, before we reach the equivalence point, the original solution in the flask is going to govern the pH of the solution, right? So the pH is going to resemble whatever is in our flask, whether that be the acid or the base. The pH at the equivalence point is going to depend on the salt that is produced, right? If we remember back to what we did at the end of chapter 17, right? After that neutralization reaction, there's going to be an ionic compound there. And depending what those ions are, will govern whether that solution is pH neutral or whether it is acidic or basic. Now, again, you can refer back to chapter 17 where we looked at the pH of salts here. And so if we have ions that are pH neutral, then of course our pH at the equivalence point is going to be 7. If we have some conjugate acid, so some positive ion, our positive ion is going to influence the pH, well then we're going to have an acidic pH. If our conjugate base, right, the negative ion, will influence the pH, then we'll have a pH that is basic at the equivalence point. Now, if we keep adding beyond the equivalence point, now at this point, whatever solution we're adding is going to be in excess, so the pH of our solution will be closer to the pH of the solution that I'm adding. So let's look at a few of these. Right, so this is a prototypical, what we call strong acid, strong base titration, right? So this is when you are, say, adding sodium hydroxide to HCl, right? And if we have a strong acid, strong base, right, we can say that the equivalence point, right, the pH will be equal to 7, right? Because if we have a strong acid, then its conjugate base is pH neutral. If we have a strong base, its conjugate acid is pH neutral, so the equivalence point will be exactly 7. And so if we look at this, we can see, right, that in the beginning, right, we get this not flat, but, a pH that is governed by, in this case, the acid was in our flask. So we're starting out at acidic pHs, and it creeps up as the concentration of that acid goes down. And then within a very short volume, right? So if this is 50 here, right, you can see that, starting, say, here and going to, say, here, right, we get a pH change from just over 2 to about 11, right? Maybe a little higher. And so we get this drastic pH change within this very small volume. And so we'll see that if we want to pick an indicator to change colors here, we don't have to be exact, right? We just have to have an indicator that is going to change colors between, the pH range around this inflection point. Because even if the color change, say, occurs, here, so let's say the color change occurs here, well, while it may not be exactly the equivalence point, if we mark that volume, it's going to be very close to the volume at the equivalence point because, again, we have a very small change in volume for a very stark change in the pH. Now, if you started out with your basic strong base in the flask and you added the strong acid, you'd get the same kind of titration curve. It would just be flipped, right? The beginning part of the pH would be basic. You'd still have that rapid inflection. You still have a pH of 7 because they're strong acids and bases. And you would end at a pH governed by what you're adding. So in this case, it'd be acidic at the end. So we get the sort of the mirror image, the flipped image of what we saw when the acid was in our flask. Now, probably the more interesting types of titrations, and the one that would mirror what you're doing in the Ka of a weak acid lab, is the titration of a weak acid with a strong base. Now, these are going to be slightly different than what we saw in the strong acid, strong base in a couple of ways. Now, we're going to focus on specifically the area leading up to the equivalence point and the equivalence point. Now, the initial pH, right, is going to be, again, determined by the weak acid. So in this case, we're saying that the weak acid here is in our flask, right? So we're adding the strong base to the weak acid. So the pH is going to be governed by that weak acid. So depending on how strong or weak that weak acid is, right, that pH is going to vary from around 2 to maybe, above 4, right, depending on the Ka of that weak acid. And we can determine the initial pH, by solving an equilibrium problem based on the concentration and the Ka of that specific weak acid that we're doing. And of course our weak acid ionization is the equation that we're looking at here. Now, as we move toward the equivalence point, but before we get there, we're going to have what we call a buffer solution. Now, we will talk about buffers a little bit later in this chapter in the next section, but the pH would be determined by that buffered solution. So this is why we don't see a huge change in the pH for these types of titrations, just like we do in the strong and strong base. We see a pretty level pH as we lead up to the equivalence point. Now, the pH at the equivalence point is, again, just like in our strong and strong base, is going to be determined by that salt, right? The ions that are in solution. So we've done a neutralization, right? So we've added our acid plus our base, and we've made water. plus a salt, right? And so, just like all of these, it's going to be dependent on the ions in that salt. So, depending on which one of those salts which one of those ions affects the pH, will determine, what's going on. But what we see is that it's going to be determined in this case, because it's the acid. It's going to be the only thing that will affect the pH, right? Is going to be the conjugate base of the weak acid, because the conjugate acid of our base, right? It's a strong base, right? So that's not going to affect the pH. So it's really going to depend on this A-, right? The negative ion in our salt. And so that will determine the pH. So its concentration will determine what the pH of the solution is. Now, what that also means is the pH at the equivalence point for this kind of titration will be basic, right? Because it's being determined by this conjugate base. Now, after the equivalence point, it's pretty much the same idea as we saw in the strong acid, strong base, right? It's going to be determined by the excess strong base that you've added, or the excess hydroxide ion. Now, at this point, the basicity from that A- ion really gets overshadowed by any of the excess strong base that you're adding. So we can just look at the strong base and look at how much we've added, and that would allow us to determine the pH at some point after the equivalence point. So let's look at this titration. So we can sort of see in the area before. Now, while it's not quite as flat as what we saw in the strong acid, strong base, we do see, only a moderate rise in pH over, quite a volume. So we're rising maybe from somewhere in the 2s here for this particular example up to around 4. So a pH unit or so. So again, this is a case we're treating it as a buffered solution. Now at the equivalence point, now notice the equivalence point is not quite as sharp here, the inflection. We have a little bit more slope there. But notice the equivalence point, right? It's governed by the weak conjugate base here. And so, not surprising, we have a basic pH, right? It's going to be typically somewhere in the order of 8-ish. And then after, it's going to be governed by how much excess hydroxide ion we've added from our strong base. But again, we have this inflection, so we have this rapid rise in pH within this relatively small volume from, say, a little over 4 in this case to close to 12, again, within that relatively small volume window. So how do we deal with these? Well, to calculate the initial pH, right, we're going to do an equilibrium problem, right, because it's based on the weak acid. So we're going to calculate a weak acid equilibrium like we saw in chapter 17. Now, leading up to the equivalence point, we're going to calculate it like we would calculate the pH of a buffer, and again, we'll get to that. And we're going to use something called the Henderson-Hasselbalch equation. So this is that equation that you'll see in the Ka of a weak acid lab, right? It looks like this. The pH equals the pKa of our weak acid plus the log of the concentration of our A-, our conjugate base, over the concentration of our HA, our weak acid. So at any point, we can determine, right, how much we have. So at the very beginning, we have all acid, no conjugate base. As we go along, right, the concentration of this acid drops down and the concentration of the conjugate base builds up. And we can figure out these concentrations with, again, an equilibrium problem. Now, we'll note here, as you'll use in the pK of a weak acid lab, right, that at the half neutralization, that the pH is going to be equal to the pKa of the acid, right? At this point, that log of A1 over HA is going to equal 0 at this point here. And so we'll talk about that when we get in a little more into buffers. Now, at the equivalence point, the moles of HA, the moles of acid, equal the moles of base, just like we saw in the strong acid, strong base. So the resulting solution is based on the concentration of the conjugate base, that is the only ion of our salt that will affect the pH. And so it's going to be determined by how much of this A minus we have. Right? And it's going to equal the original moles of HA, right? Because we've converted all of this into that at the equivalence point. And so we can calculate how much base we added. That'll tell me, I can, if I know the volume of the base and I know its concentration, I can figure out the moles of base. And I think this is now chapter 5, but and then if we know the moles of base, we can figure out the moles of HA and from there, right? And so we'll see how to go through these calculations in a bit. And we'll solve this weak base equilibrium, right? So remember, this will just be like solving, like we did with salts, this type of equilibrium. So it'd be a conjugate base equilibrium. And of course, beyond the equivalence point, it's going to be based on what the concentration of hydroxide that we've added excess. So now, just to kind of complete the picture, right, if we reverse the titration and we had our base in our flask and we had our acid in our burette and we were adding, so we had a weak base, strong acid, we get a similar curve, again, just flipped, right? So we'd start off at a basic pH and we would, again, treat it just the same. We'd have a basic buffer. We'd have our equivalence point. Now, in this case, the equivalence point would be acidic because the pH is going to be controlled by the conjugate acid of our weak base. So this is going to be controlled by, that species, our Hb plus, right? So the conjugate acid of our weak base. And it's going to be governed by the excess acid at the end of the titration. Now, if we were titrating a polyprotic acid, so one that could lose multiple hydrogens, we would see a curve here that had multiple inflection points, right? So you're going to see an inflection point for the first ionization. You're going to see an inflection point for the second ionization. So 2 equivalence points, essentially. All right. So I'm going to stop it there, and we'll come back in the next video and talk about different ways to follow it. But before we do that, I'm going to go through an example problem of how we can solve for the pH at these different points. So I'm going to do a separate video with that problem.